You know that feeling, right? When you're trying to connect directly with a friend online, maybe for a game or a video call, and it just fails. It feels like there's some kind of invisible wall between you. Well, today, we're going to tear down that wall and see what's really going on behind the scenes.
It's such a common problem. You and your friend are all set, you're ready to go, but your devices just will not talk to each other. That connection failed message, it's just the symptom. The cause is that invisible wall, and believe it or not, it has a name.
So let me introduce you to the Gatekeeper, Network Address Translation, or NAT for short. It's that little bit of magic happening inside pretty much every router in every home and office. Its main job? To take all your devices, your phone, your laptop, your console, and let them all share one single public IP address. It was a really clever way to save IP addresses, and hey, it adds a little security too.
But here's the twist. That security feature, that's our invisible wall. See, by default, your NAT works like a one-way street. It lets all your devices send requests out to the internet, no problem. But if some random connection tries to come in, it gets blocked, unless it's a direct reply to something you already sent. So when your friend's game tries to connect to yours, your NAT just goes, "Sorry, don't recognize you," and slams the door shut.
Okay, so if you're stuck behind this wall, how in the world do you connect with anyone? Well, the very first step is figuring out what your own front door looks like from the outside. You basically need to ask for directions.
And this is where something called stun comes into play. Think of a stun server as a friendly little echo service sitting out there on the public internet. Its entire job is to listen for your request and then shout back, "Hey, this is the public address I see you coming from." It's like a digital mirror for your network connection.
Let's walk through how this works, step by step. First, your computer, which is chilling on your private home network, sends a little "What's my address" packet out to a stun server. As that packet goes through your router, the NAT does its thing, swapping your private internal address for its public one. The stun server gets the packet, sees that public address, and just packages it up in a reply and sends it right back. Your computer gets it, and voila! It now knows exactly how the rest of the world sees it.
And what we're looking at here is a perfect picture of this in action. Both you and your friend, each of you behind your own protective NATs, are doing this exact same dance. You're both reaching out to a stun server to learn your public coordinates. This is the essential first move for both of you.
All right, so you know your public address and your friend knows theirs. But that's not enough, is it? You have to actually swap that information. It's like finding out your phone number, but now you need a way to actually give it to your friend.
This is where a signaling server comes in. You can think of it as a trusted middleman. You connect to the signaling server and say, "Hey, here's my public address, and I want to talk to my buddy over there." Your friend does the same thing. The server then just plays matchmaker, forwarding your address to them and their address to you. Simple as that.
Okay, the stage is set. You both have each other's public coordinates. Now for the really clever part, the trick that lets you sneak past those invisible walls.
The absolute genius of this whole thing is that it uses the NAT's own security rules against it. You know how a NAT will happily let in a reply to a message you sent out? Well, we're going to exploit that. We're going to trick both of your NATs into thinking the other person's message is a reply they were already waiting for.
This is called the UDP Hole Punch. Here's how it works. At the exact same time, you send a tiny data packet to your friend's public address, and they send one to yours. When your packet leaves your network, your NAT opens up a little temporary pinhole, and it expects a response from that specific address. And right on cue, your friend's packet shows up. Your NAT sees it, thinks, "Oh, here's that reply I was waiting for," and lets it right on through. The exact same thing just happened on your friend's side.
And just like that, the connection is made. A direct pathway has been established between you. The hole is punched.
So you might be wondering, why UDP hole punching specifically? Well, UDP is what we call a fire and forget protocol. It's like sending a postcard. You just write it and drop it in the mail. No formal connection required. That makes it perfect for this simultaneous send maneuver. TCP, on the other hand, is more polite. It needs a whole multi-step handshake to get started, but that handshake would never even begin because the hole isn't open yet for the first reply to get through. So UDP's more direct approach is the secret ingredient here.
So, why do we go through all this trouble? Why is a direct peer-to-peer connection so important? Well, because it's way better. You get lower latency, which is absolutely crucial for gaming. You get higher throughput for things like file sharing, and you don't have to rely on expensive central servers, which makes the whole system much easier to scale up.
But, as elegant as hole punching is, it's not a silver bullet. There are some types of networks, these really locked down digital fortresses, where this trick just won't work. So what happens then?
Well, the main villain of our story is something called a Symmetric NAT. This is the strictest, most paranoid kind of gatekeeper out there. For every new server you talk to, it assigns a brand new, totally random public port. So the port it used to talk to the stun server is different from the port your friend needs to connect to. The hole punch packet arrives at the wrong door, and access denied.
When hole punching fails, we have to call in the backup plan, our last resort, a turn server. Turn is pretty straightforward. If you can't talk to each other directly, you both just talk to the turn server, and it relays every single message back and forth between you.
And this visual shows you exactly what's happening. Instead of that beautiful direct line, all of your data, the audio, the video, everything has to take a detour. It goes all the way up to the turn server and then all the way back down to your friend. It guarantees a connection will be made, but it's just not as good.
And that not as good comes with a very real price tag. Running a turn server, which has to handle all that traffic, is not cheap. You can see here, whether you use a managed service or try to host it yourself on a cloud provider, the costs add up fast. That's a huge motivation for companies to make direct P2P connections work as often as possible. So we've gone through all the nitty-gritty details, but where are you actually seeing all this complex networking in action? The short answer is pretty much everywhere.
This whole collection of technologies is the engine behind WebRTC, which powers most of the video and voice calls you make right in your browser. It's totally essential for online gaming, it's the core of decentralized systems for file sharing, and it's even used in really clever projects like Tor Snowflake to help people get around internet censorship. So how does an application know which of these tools to use in what order? That's the job of the Master Coordinator, a framework called ICE. You can think of ICE as the brain of the whole operation. It intelligently tries to find the best possible path. First, it checks for a direct link. If that fails, it tries the stun-assisted hole punch. And only if that also fails does it fall back to an expensive turned relay. And the most amazing part? This whole dance happens in just a few milliseconds every time you start a call. It's incredible.
So when you step back and look at the big picture, all of this tech is really about one thing: creating direct links that bypass the big central servers that usually control our connections. And that leaves us with a really fascinating question to think about. As this kind of peer-to-peer technology gets better and more common, what does that mean for the future of the internet? Could we be heading toward a more decentralized, more direct, and maybe even a more private online world? It's definitely some food for thought.